Mi plática es en inglés. Entonces, operadores pseudodiferenciales que yo quería considerar no en español, perdón. Pseudodifferential operators are of different type of usual pseudodifferential operators. So their symbols are non-regular of limited smoothness. Application of such pseudodifferential operators gives the possibility to initiate more complicated single integral operators when coefficients are not continuous or piecewise continuous. They admit oscillation of slow oscillating type with respect to special or dual variables. So let B of x be the Banach algebra of all bounded linear operators acting on a Banach space X, and let K of x be the ideal of compact operator in such algebra. An operator A in this algebra is called Fredholm if its image is closed and the space is kernel and kernel of a joint operator are finite dimensional. In that case, the number indices is differential of dimension of kernel and cokernel is referred to as the index of operator A. A bounded continuous function on the f on the positive half line is called slow oscillating and at points 0 and infinite if for each equivalently for some lambda in the interval 0, 1, the oscillation, limit of oscillation when points tend to 0 or infinite tends to 0. The set S of R plus of all slow oscillating function forms a unital C-star algebra. This algebra properly contains the algebra of continuous function on two-point compactification on positive half line. That is segment 0 plus infinite. Suppose that Suppose that alpha and beta are orientation-preserving diffeomorphism of positive half line onto itself, which have only two fixed points and 0 and infinite. We say that alpha and beta are slow oscillating functions if logarithms of derivatives alpha and beta are bounded and these derivatives are slow oscillating on positive half line. The set of all slow oscillating shifts is denoted by these symbols. Let P belongs to interval 1 infinite. If alpha is slow oscillating shift, then the weighted shift operator U alpha, defined by the following formula, is bounded and invertible on Lebesgue space LP of R plus. And its inverse is given by the following formula. So we need substitute shift alpha by its inverse function. Thus alpha, U alpha is isometric isomorphism of this space onto itself. We consider then operators P plus minus related to Cauchy single operator. I is identity operator by this formula, where the Cauchy single operator is given by the following formula. So we fix point T, subtract interval of such form from the positive half line, and take the limit when epsilon tends to 0. So is the value of principal sense definition on Cauchy single operator. This operator is bounded on all Lebesgue spaces LP of R plus when P belongs to such interval. Let M of A denote the maximal ideal space of unital commutative Banach algebra A. Identify the point T of such two-point compactification of R plus with evaluation functionals. So we take value of A at point T. For all F continuous on such set, we get that maximal ideal space of this algebra is identified with compactification of positive half line. Consider the fibers of maximal ideal space over the endpoints 0 and infinite. These fibers are done by the following formula, where we consider restriction of Xi of that set to smaller algebra, as this gives evaluation function over point S. Now we consider the set delta with this union of fibers and 0 and infinite of maximal ideal space of slow oscillating function. And this set can be considered as closure of positive half line in the weak star closure of positive line in the dual space of slow oscillating function, subtracted positive half line. Then the maximal ideal space is the union of such set delta and positive half line without endpoints. In what follows, we write as usual a of xi is xi of a for every a slow oscillating and every xi in this set delta. Given p in interval 1 infinite, let us consider the Fredholm theory, so a Fredholm criteria and an index formula for single integral operator with shifts in slow oscillating data. First example of such operator is the following, the simple operator. We consider such functional operators, because alpha and beta are diffeomorphism of positive half line. So this is shift operator. So this is functional operator coefficients, and p plus p minus related with Cauchy single integral operator. So let coefficients a, b, c, d are slow oscillating, and alpha and beta are slow oscillating shifts. So here we have different shifts. This operator is Fredholm on the space LP of R plus if and only if the following two conditions are fulfilled. The functional operator a plus and a minus are invertible on this space. And we have influence of endpoints 0 and infinite. So in these points, we consider function m small of psi x, and this function should be different of 0 for all points psi x in such Cartesian product of delta per real line. More, this function is defined for psi in such sets, maximal ideal space of slow oscillating function, by the following formula. So this is influence of functional operators. This omega and eta is related with such function, logarithm of alpha t divided by t and logarithm beta of t divided by t. So this exponents of derivatives. And this is influence of operators p plus minus related with Cauchy single operator. By the way, this function is a symbol of Cauchy single operator in space LP of on real positive half line. So we have such two conditions of the Fredholmness. But to obtain these conditions, we need to use pseudo-differential operators of, with more general classes of symbols. Okay, let A, B are slow oscillating. We say that B, I dominates B, and write by this symbol if this function is separated from 0, and the limit of such differences when t tends to 0 and t tends to 0 are positive. Then we consider this function. This function is A if A dominated, or B is B dominated. This is related with the following property of binomial functional operators, that conditions of their invisibility are alternative. So suppose that A, B are slow oscillating and alpha is slow oscillating shift, then functional operator is invertible on this LP space if and only if or either A dominated B or B dominated A. In first case, when A dominated B, then inverse operator is given by such Neumann series. So in this case, spectral radius of operator B entre A multiplied by U alpha is less than 1. So this is less outside of this, behind of these formulas. If B dominated, then we need subtract U alpha, and then operator A entre B and U alpha to power minus 1 again has spectral radius less than 1, and then we have the series for inverse operator. So we have explicit formulas for inverses of such functional operators. Now we need to use almost periodic functions. This function generated in algebra L infinite of real line by exponents with arbitrary real lambda. Semi-almost periodic function, this abbreviation, stands for C-style algebra of all semi-almost periodic functions generated in these algebras by all almost periodic functions and all continuous functions on two-point compactification on the real line. Defining this function as before, and such set, we conclude that Fredholm criterion of this function, if we fix tau and consider with respect to dual variable, are semi-almost periodic functions. These functions are invertible for all point tau in the positive half line sufficiently close to endpoints 0 and infinite. Then we use the following definition of generalized Cauchy index. So we know that the Cauchy index, if function is invertible and continuous, is we can take argument, increment of argument over segments, and with normalization times to 1 over 2 pi. Now this function is semi-almost periodic, so it has oscillation and points 0, minus, and plus infinite. So in this case, this index is defined by the following formula. First, we use Bohr theorem on the argument of almost periodic function. This is a linear function and almost periodic. We subtract linear part. So this function phi plus minus are almost periodic. Then this operation replace slow oscillation but values, constants. And we consider usual Cauchy index with difference of values in plus and minus infinite and normalized by this multiple. So this result was obtained by Viktor Kravchenko and myself in such year. The generality Cauchy index has the usual property of Cauchy index. So this index exists for every invertible semi-almost periodic function, is finite, independent of the branch choice of argument, stable under small perturbation, and has the logarithmic property. So if both functions are invertible and class of semi-almost periodic function, then its generalized Cauchy index is sum of indices of each function. So, and this gives possibility to calculate the index of Cauchy single interpolator with shifts. First, I consider old result obtained jointly with Viktor Kravchenko. When all data are continuous, so coefficients are continuous on such set, and derivative also are continuous. If the operator M with binomial functional coefficients for p plus minus is Fredholm on such space, criterion was given before, then its index is calculated by the following formula. So we consider a function with dominated coefficients, takes the increment of arguments, and add influence of almost periodic, of generalized indices of semi-almost periodic function and plus and minus infinite. So this is denotes increment of argument of this invertible function when point traces such set. Now, this result was generalized jointly with my son and Lebre, this is mathematician of Portugal, for slow oscillating data. Let A, B, C, D are slow oscillating function on positive half line. Alpha and beta are slow oscillating shift. If the operator M given before is Fredholm on such space, then in index calculated by the following formula. So this part is almost the same, but now these functions are slow oscillating. So we don't have limits in 0 and infinite. To this case, we need substitute all the half line by such segments when tau is bigger than 1, and then calculate all the over such results. This index calculated over boundary of rectangle, finite rectangle, and then consider limit when tau tends to plus infinite. So when these points approaches 0 and approach 0 and infinite. So this is a generalization of index formula. So here we need to take to account that these functions are semi-almost periodic, and these functions are moreover invertible in such set. To this case, such indices are calculated. Now, let us pass to pseudo-differential operators. So this technique which lies behind of such consideration, which was indicated before. So if A is absolutely continuous function of finite total variation on this half line, then we know that this derivative is class L1, and the total variation gives the following formula. Let V of R be the set of all absolutely continuous functions of finite total variation on real line. This is Banach algebra if the norm is defined as sum of norm and infinite of symbol and total variation Now we consider a set of symbols of pseudo-differential operator. So this function depends on two variables. Special variables run through the positive half line. Dual variables run through the real line. So this set of all bounded continuous functions, VR-valued function defined on the positive half line. This again is a Banach algebra of all bounded continuous function on with the following norm. So we take V norm with respect to dual variable, then supremum norm with respect to special variable. So this is set. As usual, this symbol is the set of all infinite differential functions of compact support on positive half line. Then we consider normalized invariant measure on the positive half line. This symbol is belong to that class. Then the Mellin pseudo-differential operator, defined by this symbol, defined by the infinite differential function of compact support by the iterated integral. So we take Mellin transform, multiplied by this function, takes inverse Mellin transform. But symbols depend now of two variables, not only of the variables convolution operator. So this pseudo-differential operator, we have dependence on the real line of variable, special variable. This operator extends to a bounded linear operator on this space for any p in interval 1 only, and the norm of this operator is controlled by the norm of symbol in such class. By the way, this result was generalized with dependence of special variables is of class of L infinite. So when this function is a bounded measurable VR-valued function, this result remains valid. To prove this, we need the proof is not simple, and they use semi-additive function, etc., etc. So now we consider symbols which are slow oscillating with respect to special variable, and with dual variable are VR-valued. Then this is the Banach subalgebra of this. And symbols are slow oscillating and zero and infinite. What this means? So in this case, we consider slow oscillation, but now we replace absolute value by the norm, L infinite norm with respect to dual variable. Take this this is oscillation maximum, and this maximum should tend to 0 when R tends to 0 or infinite. So this class of slow oscillating symbols. Now we consider subalgebra, Banach subalgebra of VR-valued function, which belong to this class, but moreover satisfies the following condition. So with respect to dual variable in VR norms, these are continuous. When H, this symbol here, is given by the following formula. And we need small Banach subalgebra E tilde of R plus VR-valued of all functions in that algebra, which possessing the property. Possess the property that slow oscillation over interval minus infinite minus m and m plus infinite tends to 0 when m tends to 0. So these intervals become smaller and smaller. This again is, so this set can say us about compactness of pseudo-differential operator. This set is used to construct Friedman theory, so to obtain Friedman criterion and index formula for pseudo-differential operators. Now about compactness. If both symbols belong to this algebra, then semi-commutative is compact on any such Lebesgue space. If both symbols are, this is corollary of previous one, then the commutative also is compact. And moreover, if symbols degenerate over the boundary of such rectangle, so if this condition is fulfilled, then pseudo-differential operator is also compact on any Lebesgue space. So these three results on the compactness. Now about Fred-Goldman and index of matrix Mellin pseudo-differential operators. Let me consider matrix symbols in such class with E tilde. Then the Mellin pseudo-differential operator is Fred-Goldman on such space if and only if this symbol is not vanish on the blow-up boundary of such rectangle. So this function with respect to dual variables has limits in plus minus infinite. So this is respect on special variable, and special variable runs through this positive half line. determinant of this symbol is not 0 for all such values. Now we calculate symbol and endpoints, but endpoints with respect to special values, symbols have slow oscillation. So they have a lot of partial limits, and these partial limits are parameterized by point psi of this union of fibers of maximal ideal space of slow oscillating function. So this determinant for all such points also is non-zero. So we have non-vanishing condition on the horizontal paths and vertical paths. So in this case of Fred-Goldman's index is given by the following formula. So we take determinant and take argument over this rectangle when the points run through this boundary counterclockwise, and take the limits when m tends to 0. So this rectangle is a usual rectangle of R plus by R. So, and we obtain information about regularizers of Mellin pseudo-differential operator. So if A belongs to this class, and Mellin pseudo-differential operator with such symbol is Fred-Goldman on such space, then each regularizer has the following form. Mellin pseudo-differential operator plus compact operator. K is compact, and these symbols again belong to this class. And we know these values on the boundary of rectangle. In any part, this is arbitrary values because such operator is compact. So this influence of any part of rectangle is included in compact operators. Now let A be the Banach algebra of all bounded linear operators in such space, generated by identity operator A and by the Cauchy single integral operator S. Consider such isometric isomorphism. So phi is the isometry, so we replace function ft times by this power, and consider such similarity transform with respect to phi. So these things give us possibility to relate Cauchy single integral operator with Mellin pseudo-differential operator. Now, what is the relation? Let P belongs to such interval. For every y in interval 1 infinite, the function Sy, defined by the following formula, belongs to the set of all Fourier multipliers of the real line in space LP, and Cauchy single integral operator is similarity transform of Mellin convolution operator. So Mellin convolution operator as given, first we apply Mellin transform, then times to this function, and apply inverse Mellin transform. This is true if P equals 2. When P is not equal to, we need to consider this jointly, this not product of three operators, and this we first consider for symbols defined on LP intersection with L2, so we know what this object, and then consider extension by continuity. This gives the definition of Mellin convolution operator. Mellin pseudo-differential operator are generalization of Mellin convolution operator. So we have such simple representation via Mellin convolutions of such functions. For every y is such interval, the function Ry, defined by the following form, also belongs to the class of Fourier multipliers. And single integral operator now has fixed singularity in 2 points, and 0 and infinite. It's given by the following formula. So for simple situation, this equals 1 when y equals p, and we have such, instead of Cauchy single operator, we have difference here, but here we have plus. So this symbol is equals 1 only in point 0 and infinite. So in other points, this operator is locally compact. So this again belongs to the algebra A, generated by identity operator Cauchy single operator, and this is again related with Mellin convolution by this formula. And third property is this algebra is commutative, and we have a relation between this operator and Cauchy single operator by the following formula. Okay, now we use this symbol to say that difference A minus B is a compact operator. And if alpha is slow oscillating shift and A is Cauchy integral operator with constant coefficients, then such products commute up to the compact operators of this operator and this inverse with arbitrary singular integral operator with constant coefficients. Now we consider special symbols. They are very important to study singular integral operator with shifts. So suppose that omega is a slow oscillating real valued function. Then for every p in such interval, this function is product of this function. This function vanishes at point 0 and infinite, and all other points is continuous, times to this function which oscillate. And this product is again a function which vanishes in infinite, but this function belongs to this algebra of symbols, of pseudo-differential operators. This part is important. And moreover, we have such estimate of norm of symbols via supremum of function omega. Function omega is a logarithm of shift alpha t, omega t, alpha t divided by t. So in sense is logarithm of derivative. So now let alpha slow oscillating shift or alpha be associated isometric shift operator on such space. For every y in interval 1 infinite, this product of singular operator with fixed singularity and 0 and infinite by this operator can be realized in Mellin pseudo-differential operator. So if we use such similarity transform, instead of convolution, Mellin convolution, we obtain Mellin pseudo-differential operator, because this symbol now depends on two variables, special variable t and dual variable x. So this dependence is given here. But because omega is slow oscillating, this term tends to 0 when t tends to 0 or infinite. So actually, such dependence is this product is mean as a principal part of this product. Omega is given here. This symbol belongs to this algebra of symbols, and up to compact operators, we have the following. This operator is given by Mellin pseudo-differential with simply symbol of such form. Okay, now how to study Fredholmes and index? So we need to use special operators given by the following formula. G alpha and G alpha minus 1, where shift operator is replaced by its inverse. In symbol, shift alpha is slow oscillating. These both operators are Fredholm on space LP, and their indices equal 0. Now, to prove this, we use the following relation. These products are Mellin convolution operators, Mellin pseudo-differential operators, when symbol G tilde is given by the following, when C equals 1. So we have such representation. And here we use a homotopy with respect to theta. This gives possibility then simplify then and calculate index of such that index are 0. Next, for every y in interval 1 infinite, the Banach algebra A generated by such operators contain, along with such operator with fixed singularities, also weighted Cauchy singular operator. So appears such multiple. And we consider corresponding operator P plus minus with such as replaced by this one. For all A slow oscillating, if one dominate A, so this condition is fulfilled in points 0 and infinite of positive half line, then we have another ingredient to study Fredholmes of general Cauchy singular operators of M, which was in the first slides. So if these coefficients are slow oscillating and dominated by 1 both, then this operator, when y is now 2, is important. But this operator we consider space LP. In this case, when we replace P here by 2, index of such operator is 0. This operator is Fredholm and index is 0. Now, if y belongs to this interval, V is slow oscillating function, gamma is slow oscillating shift, then this product of Cauchy singular operator with fixed singularity and functional operator can be realized as Mellin pseudo-differential operator with such symbol. And this symbol belong to this algebra, and moreover, this symbol vanish for all point t on the R plus. Only in endpoints we have dependence here, but this dependence parameterized by point psi on the set delta. So we have this. So on vertical line, symbol is non-zero. For in all other part, symbol is 0. Okay, now we have the same, but for inverse operator. So we assume that this functional operator is invertible. Then this object is well defined. But this again can be realized as Mellin self-differential operator. But now symbol is series. And all the terms in this series belong to that class. So the symbol belongs to this class. And again, symbol is non-zero only on vertical paths when psi belongs to this set. Okay, now what is one of the results of this form to illustrate? So suppose that P belongs to such interval, epsilon 1, epsilon 2 are or plus or minus 1, alpha and beta are slow oscillating shifts. Suppose that this function is slow oscillating and 1 dominate B and D. Then these operators, each such operator is Fredian on such space, and index of such operator is 0. Moreover, we can give the explicit form of up to the complex operator of its regularizer. So operator is Fredian if there is its regularizer. So operator such that initial operator times to that operator for both sides gives identity operator plus compact operator. So this regularizer is the following. We have dependence on Mellin convolution operator, Mellin self-differential operator, when function phi is given here. So we have dependence of symbols Cauchy singular operators here and here, and dependence of shifts and coefficients of shifts evaluated in points at points psi. So, and then times to such operator with inverse operator. So this is a regularizer for such operator. Now another applications. So we consider complicated functional operators. Now we assume that shift alpha is slow oscillating, coefficients are slow oscillating positive half line for all k integer, and we consider Wiener algebra functional operators. So this operator is represented by such series with respect to powers on shift operator. So it is a generalization of Fourier series, but as operators. And Wiener norm, so this is a series of norm coefficients and infinite, is finite. So given P, we can let us study Fried-Gormez on the space LP of R of non-local singular operators of the form. So we have such functional operators as coefficients, and this dependence of Cauchy singular operator S. With such operator, we associate the function defined on this Cartesian product by the following form. So we have here series, we have dependence on two variables here, and this dependence of dual variables with respect to Cauchy singular operator. Omega is logarithm of such P plus minus given by the following form where we calculate symbol for in space LP of Cauchy singular operator. Then if we fix x, then this function is slow oscillating with respect to special variable. So taking Gerg-von transform, we extend this function to all this set. So we have dependence of psi when psi runs through this union of sets. And this result was obtained jointly with my PhD student, Gustavo Fernandez Torres. So let P belongs to this set, coefficients are slow oscillating, alpha is slow oscillating shift, then the operator n is Fredian in such space if and only if two conditions hold. The functional operators are invertible on such space. If to recall two previous results, this was binomial functional operators. And the function A, with such more complicated form, is separated from 0 for all psi in such union of fibers of slow oscillating function over point 0 and infinite. This theorem remains valid if this condition we replace only that such values are non-vanishing for all such things. Here is separation, here is condition simpler. But such conditions are equivalent. Now, what about the invertibility of functional operators? So let alpha is slow oscillating shift. We consider iteration of shifts for all integer n and all point t of positive half line, fixed point tau and positive half line. Let gamma be a semi-segment within point tau, alpha tau. When this point is included, alpha of tau is excluded, so semi-segment. Now, if we consider limits of such iteration for any point tau and positive half line, then these limits are the same, this point tau plus minus, and this tau plus minus belong to this set. Now we consider Banach space L small p over z, so all integer numbers with usual norm, and to each such functional operator we may associate a matrix function. Matrix is infinite dimension on both sides. So this matrix has the following form. So in a sense, the structure is by diagonal, in each diagonal we have iteration of coefficients. So it's so-called band-dominated matrix. So this matrix function with such values for all point t of real line is a bounded continuous BLP valued operator function, and its norm is maximum of norm in each point t when t runs through positive half line is less than or equal to norm or Wiener norm of functional operators A. Now we consider projections Pn plus minus when these symbols is given in the next slide. So this is given by the form, so characteristic function on the z, and result of criteria of invertibility. The functional operator, Wiener type functional operator with slow oscillating coefficient, slow oscillating shift, is invertible on the space LP for any p in segment 1 infinite, if and only if these symbols is non-zero for every psi in such set and every point z in unison. This is Gelfand transform of limit operators and points. But because we have slow oscillating behavior, we have a family which depends on point psi, which runs through this set. This is all the partial limits of coefficients. With respect to z, we have Gelfand transform. So this is for z is dual group, which is a unit circle. And this is interesting that if we calculate Cauchy index, so we take increment of argument when z runs through the positive line and normalized by this multiple, then these numbers not depend on psi, depend only on point tau plus minus. So in point and points. But for all the points, these values are independent of psi. Then there exists number n0 such that for every t in semi-segment tau alpha tau and every n bigger than n0, this operator, now I would like to show what are these operators, is invertible and determinant of such function is non-zero. Now what about such symbols? So this with such operator we may correspond operator a script of t. So this infinite matrix function band dominated. Now we divide this matrix by blocks 3 by 3. But such blocks are in the general central block is not quadratic. But if we consider invertibility, the central block is quadratic. So these outmost blocks form this matrix function. This is invertible. And the crucial part of these things prove that such blocks are invertible. To prove this result, we use a special factorization functional operators of family of matrix function depending on parameter psi. So this is difficult and crucial part of the proof. Then, because these blocks are small in the norm, So this operator is invertible. And now we need to consider what is modified central block. Modified central block is given here, and this matrix function should be non-zero. Determinant is not zero, so it is not singular. And this finish this part. Now another application of pseudo-differential operator to single operator. This application to boundary value problem, which calls Haseman boundary value problems. And this is given by my chief, Professor Litvinchuk, in his book, old book 64. And to find a function phi analytic in a complex plane without closure of curve gamma, represented by Cauchy integral operator over curve gamma with such density on space LP and satisfying the boundary condition. So this problem is related with problem of gluing of surfaces when we have some points not the same for two sides of this related gluing point T with point alpha of T. So this is have application, this problem in theory of gluing the surfaces with boundaries. So this boundary condition, phi plus and phi minus, are angular boundary values of phi on gamma. G is a bounded measurable function. G small is a LP function on the curve gamma. By the Schotsky-Preliminary formulas, the relative operator plus minus, these Haseman problems can be reduced to equivalent single operator with shifts. So now we have such symbols, functional operators. Here we have coefficients. So it is simple as it before. This operator is shift operator, so we don't normalize. This is not isometric. P plus minus, given by the same formula as before. And B of x is Banach algebra for all bounded linear operators on the Banach space X. Now, we consider more general contour. So these logarithmic stars. We have each curve gamma k is a logarithmic spiral with the indices of spirality is spiral likeness delta. And all beta is angles between them. So this, we have different logarithmic spirals. This is Carlson curve, so this condition is fulfilled. We have portion of the curve measure of curve in the disk of center at T and radius epsilon, divide by epsilon, take such supremum. This supremum is bounded. So this Carlson or a force David curve. Now we slow oscillating shifts as before, but now the shifts act on each curve separately. So we assume that the logarithm of absolute value is bounded continuous function. This gives boundedness of shift operators in its inverse. We call this shift slow oscillating in points 0 and infinite. If for every parameter r in such set, we have the following condition. When this omega are real valued function and one times continuous differentiable, and this function also is slow oscillating. Now we have these following properties with related with slow oscillation of omega k and phi k. And if alpha is slow oscillating shift, then we have such formula for the derivative, and we have the following condition for the shift. Slow oscillating coefficients. So this given on the axis, we parameterize by the parameter r, which runs through the whole line. This function is slow oscillating. Then, given P, we consider Banach space vector value now of such vectors with entry in such space and with this norm. If P belongs to this interval, gamma is logarithmic star. By analogy with our works with Albrecht Bircher and Vladimir Rabinovich, we introduce such isomorphism. As before, only now we have, because contour is a union of n arcs, we have vector valued space. Gamma is Carlson curve, single integral operator is bounded, and now we consider what are psi images of Cauchy single operator and commutators of that. They are Mellin pseudo-differential operators. And now I would like to show symbols. So we consider important function in such algebra. So this is cotangent of that. When delta equals 0, we consider real line. In this case, we have as before, but now such denominator appears. Dependence of shifts here. These angles of depends of angle of such logarithmic star, and this is symbols 1 over z, symbols of Cauchy single operator with fixed singularity, but defined on the logarithmic spiral. And this is dependence on shifts omega. So we have that one. All these symbols are in such class, and we have some estimate. Now, what about the image of Cauchy single operator? This matrix function on diagonal entries have the following form. Off diagonal entries have the following form. So this is dependence on angle. This function is calculated. This symbol is calculated by the following formula. Sine, hyperbolic sine tends to infinite and points plus minus infinite. So the symbol vanish and 0 and infinite, this quotient. And this function gk are valued with respect to dual variable, and symbol of Mellin pseudo-differential operator belong to that class for all entries. Now, what about product of Cauchy single operator by shift operator? This object has a problem. The diagonal entries are not Cauchy single operator and not a pseudo-differential operator, but of diagonal entries. So we have this condition, are symbols of that class. So to study commutators, we have again Mellin convolution, Mellin pseudo-differential operator. Now, results. If G, for Haseman problem, if G is low oscillating function, this operator is Fredholm on such space if and only if coefficients is separated from 0, and determinant of such symbols lim inf of infinite of z is bigger than 0. So psi of gamma is operator multiplication as diagonal matrix with values in each entry, but this is functions, are functions low oscillating. This object is calculated by the following formula, where p plus minus is given here. So this condition is equivalent to condition of that form. So when we have infimum only in vertical parts of the rectangle. And we have the following lemma. If gk of xi for all xi are non-zero, and for all k, or for all x, then this equality is holds if and only if this condition is fulfilled. So we need take this function dependent on two parameters, eta and lambda. Depends of eta. This dependence of logarithm of derivative of shifts, omega k. Here we have dependence of coefficients in lambda. And this, here we have index of spiral likeness. So we have such complicated formula. And if this symbol is not integer, then this condition jointly with z is fulfilled. Now, Fredholm condition can be rewritten in such form that coefficient is separated from 0 and this function is non-zero for all xi in delta. Now but this function determinant t of xi with respect to dual variable is semi-almost periodic. So we need to calculate generalized Cauchy index, and this generalized Cauchy index is given here. So E means the integer part of such number. So we can calculate for all points xi these things if the following conditions are fulfilled. And final slide, index formula for Cauchy single operator with shifts t, which related to Haseman problem. If t with such coefficients is Fredholm on such space, then index of t given by the following formula as before, but now we rewrite this formula in terms of phi. So this is an increment of coefficients over x, but we need to consider segment m to power minus 1 m. Then we apply argument of lambda of coefficients here and calculate and apply generalized Cauchy indices of such function phi. And take a limit when m tends to 0. Then we have index Fresnel index of such operators. That's all. Thank you for attention.